There's only two things you need to know to successfully solve parallel pipe flow problems. Of course, actually implementing those two things is going to be some of the longest, most tedious problems of the entire fluid mechanics course. So I just want you to keep that in mind as we go through this problem. It's not super difficult, it's just long and boring. I always set up fluid mechanics problems with given, find, concept, assumption, solution. And for this problem, I'm going to try to adhere to a color standard of purple for path ABC, that's the top thinner path, and then green for path ADC, which is the thicker 1-inch pipe path. As you can tell from looking at the picture and reading through the problem statement, you can tell that this is going to involve minor losses because of the T-joints and the bends. We're given a value which I've called E, which is usually written as epsilon, which is a roughness coefficient. So that's a clue that this is going to require use of the Moody Diagram for friction coefficient for major losses. But our goal is to figure out of the 67.3 gallons per minute going through this system, how much of that flow is going to take the thin top path and how much of the flow will go through the thicker, longer bottom path. And here we go, equations 1 and 2. These are the only two things you really need to know. So since there are two unknowns we're trying to find, QABC and QADC, which I might just call purple Q and green Q. So the two things that we know is that when we add together the two flow rates, they have to add to 67.3 gallons per minute or 0.15 cubic feet per second. And the second thing is that head loss along both paths is going to be equal. If you envision doing the energy equation from point A to point C, it doesn't matter which path you take. You have to get to the same result at C either way. At point A, there's some velocity and some pressure, and point C, there's a different velocity and different pressure. And so there's head loss between A and C. Let's imagine that the head losses were different, just to see why that wouldn't work. Imagine the total head, that is between pressure, velocity, and elevation, the total head at point A was 100 feet. And imagine there was 10 feet of head loss along the small upper path from ABC. And imagine there was 20 feet of head loss from the lower path, ADC. So then the upper path from the starting at 100, losing 10 feet, you'd be at point C should be at 90 feet of head. But starting at 100, taking the lower path and losing 20, you would have point C at 80 feet of head. Point C can't be at two different pressures, right? Once the fluid streams have combined, it is just one number. So the head loss between the two paths has to be equal. And the way that this happens is that fluid will change how much goes through either path in order to equalize the head loss. Imagine in this scenario, again, where there's 10 feet of head loss up top and 20 on the bottom. If there's so much extra friction down at the bottom that it would create so much extra head loss, the system would equalize itself by instead some of the flow, instead of keep going downward, would divert upwards. And by pushing more flow through upwards, I would be going at a higher velocity and have higher head loss. And then the bottom path, since it has less fluid flowing through it, might have less velocity and less head loss. And so what's happening is the amount of flow will fluctuate in order to balance the amount of head loss in every path. Well, your TA Indy certainly agrees that these problems can be tedious because he's already waiting back there to play to take a break, but Indy's gonna have to be patient because we still got a long way to go. So two types of head loss. We've got major losses due to friction and minor losses due to all of the T-joints and the bends, the 90-degree corners. This FL over D, V squared over 2G, you've probably seen this before written as the Darcy Weisbach Equation. So L is the total length of pipe that friction is acting through, and D, the diameter of the pipe. And over on the minor losses side, K is going to be just a coefficient that you'll look up for each source of minor losses. So the purple path has two T-joints and two 90-degree angles. We don't have a lot of information to tell exactly what's going on in these 90-degree angles, but knowing that this is half-inch diameter pipe and just looking at the picture, I'm gonna guess that these are actually threaded rods. So looking at my table, I'm gonna grab 0.9 for the 90-degree angles. And for the T-joints, if you're just going straight through the T-joint, that would be the straight run, the 0.4. But if you're going through the 90-degree angle part of the T-joint, that's this value 1.8. Now I can probably make an argument that the loss here should be even larger than 1.8 because not only are we going through a T-joint, there's also a contraction happening. So based on the picture, it looks like we're going from point A, a thicker pipe, down to point B, which is thinner, and this change in thickness happens inside the T-joint. But let's keep it simple and just use the numbers given to us in the tables. If I wanted to make an assumption and choose a value a little bit higher, like 2.5, and I could just write in there why I'm justifying that use. So I think either option would be okay here. One, choose the best number you have, which in this case would be 1.8. Or write a brief comment as to why you're using a different number. So I might use 2.5 and say 1.8 plus a little bit extra to account for the sudden contraction inside the T-joint. Right, so we can plug in similar numbers over on the green side where they also go through two T-joints, again, at the sort of 90-degree angle T-joint, so that's the value 1.8. And there's 4 regular 90-degree corners, so 4 times 0.9. Because again, I'm assuming that those are threaded rods also. So equation 1, this is the head loss terms. These are equations in terms of velocity. My equation 2 is in terms of flow rate. The two volumetric flow rates have to add up to the given number. If I want this to be a 2 equations, 2 unknowns, I need to convert those volumetric flow rates into velocities. So I've got 2 equations and 2 unknowns. So calculate the cross-sectional area of each pipe, and Q is equal to velocity times area. Rearrange and solve for my 2 velocities over on the right-hand equation number 2. And now here's where reality starts to sink in a little bit. This head loss equation still has F, the friction coefficient, as unknown. I'm going to get the friction coefficient from the Moody diagram. So in order to use the Moody diagram, I need the Reynolds number. And in order to get the Reynolds number, you see where this is going, I need to already know the velocity, but the velocity is the thing I'm solving for. So this problem requires an iterative solution. And iterative solutions are the worst kinds of solutions because this means that you are just going to guess, solve the answer, figure out whether you're wrong or how wrong you are, because you're always going to be wrong the first time, and then guess again. And then you're going to keep repeating that until you end up actually guessing the right answer, or you just get bored of it and decide that you're close enough. So looking at equation 2, so to even figure out what sort of order of magnitude to guess, I'm going to look at equation 2 because that seems to be numbers at sort of a real life scale. We've got VABC plus 4 VADC equals 110. So if both velocities were around 20, that would kind of make sense, right? 20 plus 4 times 20 is about 100. Is exactly 100. So let me just start off with that. I'm going to guess that VABC is equal to 20. I have no reason to think that this is correct, but you just have to guess something. Just pick something. It doesn't actually matter. You're going to be wrong. Just pick something. So I can plug that in, solve for the other velocity, 22.49. Now we're going to use these 2 velocities to find our 2 Reynolds numbers so that we can go to the Moody chart and get friction factors. And then once we have the friction factors, we'll end up solving for this VABC. And if we happen to be magically awesome, we would get 20 for VABC. And if we don't get 20, then we'll know that we have to try again. So to use Reynolds number, I have to look up viscosity in a table. And for D in the numerator, the diameter, I need to make sure that I'm working in feet because that's what all of my other units are. I get 7.9 times 10 to the 4th for purple Reynolds number. And 1.78 times 10 to the 5th for my green Reynolds number. So normally for roughness coefficient, you would be given the material that the pipe is made out of, whether it's commercial steel, galvanized iron, copper, something like that. And you would look this value up in a table, but for this problem, we were given the number. So awesome, I guess that saved us like 10 seconds. And for these, the hardest part of the roughness coefficients is keeping track of how many zeros you have in front of your number. So 0.00192, just 2 zeros for the purple number. 0.00096, so 3 zeros for the green number. So jump over to the Moody diagram. 0.00192 is a little bit below the 2. And then 7.9 times 10 to the 4th on the horizontal axis. You find the 10 to the 4th and then go further to the right to 7.9 because where you see 10 to the 4, that is 1 times 10 to the 4. And the numbers after it to the right of it are like 2 times 10 to the 4, 4 times 10 to the 4, etc. So trace these up where these 2 lines meet, move over then to the left side of the drawing. To me, this looks a little bit above the 0.025. So I'll call this 0.0257 because it looks like it's closer to the 0.0256 line than 0.25 line For green, we find 1.78 times 10 to the 5th on the horizontal axis. So 0.3096 will be just below the 0.201. And these look like they're just barely above the line, so I'm going to call this 0.0211. It's okay if your F values when using the Moody diagram don't exactly match my values. It is a little bit hard to read, especially when you're in this curved section. You're kind of interpolating in between these curved lines for the roughness coefficient, so it's hard to see exactly where it's at. But do your best to try to get as exact a value as you can. And try to also be consistent, especially since my numbers are definitely not perfectly accurate either. And look how squiggly each of my lines are, right? Just do the best you can. So go back to our equations. We've got the two F values. So now on the left, the head equation, I plug in both F values, and I also plug in the 22.49, which was the VADC. And what I'm solving for is the thing that was my initial guess. I guessed a value of 20 for VABC, and now I want to solve for VABC. And if I guessed correctly, the value I get should also be the same as my initial guess. And of course, that's not what happened. That's never going to happen. VABC of 26.9. At least I'm on the right order of magnitude, but this is not close enough, right? This is over 25% error, which means we have to repeat the process again, solve for a new Reynolds number, go back to the Moody diagram, new friction coefficient. So this problem isn't unusually difficult. It's just massively annoying. So your TA Indy doesn't like having to repeat steps, so he's back here taking a nap while we go through this iterative process. So if you're like your TA Indy and you hate having to redo work over and over again that you already did, go ahead and hit the thumbs up and I'll let him know that you agree with him. So new guess, VABC of 26.91. Solve for a new VADC and get 20.77. Get new purple and green Reynolds numbers. So we've got 1.07 times 10 to the 5th. And 1.65 times 10 to the 5th. There's one step that doesn't have to be repeated, the roughness coefficient. At least we can use the same value we had before for that one. So let's jump back over to the Moody table. So same roughness coefficient over on the side, but a new Reynolds number. So we're shifting left or right. So with the new purple line being a larger Reynolds number, we're getting a lower friction coefficient. This time looks like 0.0248. And now a smaller Reynolds number for the green line means it's a slightly larger coefficient. So I'm calling this 0.012 because it's actually really close. And so this is where it's kind of okay if your numbers aren't perfectly accurate, like if your numbers don't perfectly match mine. As long as you're consistent with yourself, as you iterate through this problem, you'll get closer and closer to a final answer as long as your numbers are self-consistent. That is, my green lines are almost the same, so my two green numbers are almost the same. It's okay if they're both wrong by the same amount, as long as I'm changing in the correct direction. That is, this time I should be a slightly higher number. Even if 0.0211 was wrong before, the fact that I'm moving slightly in the upwards direction is still going to get me closer to the answer, even if I'm not reading the diagram perfectly. Back to the equations, plug in the new friction coefficient, plug in the new VADC, and solve for VABC. Fingers crossed, 26.91, big money, no whammies. 25.1. And I think maybe this is not quite close enough. From 26.9 to 25.1 is still about a 10% error. So let's go one more time, but I got a good feeling about this next one. We use 25.1 as the next guess, because again, there's no real easy way to tell whether it should be higher or lower. So we solve for VADC, 21.2. Get a new purple Reynolds number. It's a little bit smaller this time, 1.0 times 10 to the 5th. Get a new green Reynolds number, 1.68 times 10 to the 5th. And that one has barely changed at all this time. So that's kind of a good sign that the numbers are not changing very much. That means you're getting close. And in fact, this number is so close to the last one, I'm actually just going to use the same green friction factor, 0.0212. So we're really only looking up a new purple number this time. So new purple line is in between the two other purple lines. And in fact, this one looks like it's intersecting right on the money, right on the line. So I'm going to call this one exactly 0.025. And now I really want to be done with this problem. So I'm plugging in my new friction factors and my same green friction factor, my new VADC 21.2, and I am giving all of my willpower into the calculator to make this value equal to 25.1 because I want to stop finding Reynolds numbers and stop using the Moody diagram. I want to be done. And I get a value of 25.6. And that makes me ask myself, how close is close enough? And that's going to be different for every problem you solve. It's going to depend on if this is a homework or a test, or how big of a jerk your professor is. If you're a working engineer, it's going to depend on what side, maybe what type of safety margin you have. So 1% of 25 is 0.25. So 0.5 is a 2% error. And I think for a YouTube video, 2% error is definitely close enough. If you wanted to keep going, just put in 25.59, guess again, and you'll see how close you get. I think probably in 1 or 2 more steps, you would get it to at least 3, if not 4 significant digits matching. So we're probably actually getting pretty close, right? 2% error is probably pretty good, actually. And as a general rule of thumb, I would usually say that 3 iterations is usually enough to demonstrate to your professor that you know what you're doing. So if you go through 3 iterations and it's kind of close and you think you've done them correctly, then I think your professor should give you credit for that because you've clearly demonstrated that you know how to solve this type of problem and you avoid having to do this 4, 5, 6 times because that won't demonstrate any extra learning. It'll just take up more of your time. Oh yeah, the problem's not actually over. Man, all that celebrating from having to deciding to finally stop, look back up to given find concept. The thing we were trying to find was Q in gallons per minute, not velocity. All right, a couple extra steps. So scroll back up the page, find my area values because Q is going to be velocity times area. And our velocity times area is going to be in feet cubed per second. So we're also going to have to convert seconds to minutes and feet cubes to gallons. I don't usually fault students for forgetting a lot of conversion factors, things like BTUs, because they just don't come up very often. But the conversion from gallons to feet cubed is literally LEET, 0.1337. So as long as you're not a noob, you should always remember how to convert cubic feet to gallons, 0.1337. Plug in the numbers, the purple flow rate, 15.7, and the green flow rate, 51.9. So anyone paying close attention will recognize that our numbers add up to 67.6, not 67.3. And that happened because I was lazy and I celebrated and I just decided to give up on this problem and decide I was close enough. But this is how you can recognize how close we were. So if we had kept going, we should have gotten maybe after 1 or 2 more steps an answer that's a little bit closer to 67.3 when we add those 2 up. But I still think that this is close enough, usually stopping after 3 steps. That's going to be good. If you haven't already bookmarked my fluid mechanics playlist, I've got that up on the screen right now. Go ahead and click on it and just bookmark it in your internet browser. And that way, come final exam time, you'll have it saved and ready and you can jump back in and review any topic you need to get ready for your final.